Hi guys, welcome back to lesson number 13. We're talking about total change. Today we're going to talk about rectilinear motion, and really what that means is talking about particle motion again. I wanted to say really quickly about before we get to these equations that what you guys learned in the previous lesson is something called fundamental theorem of calculus. So if I were to take my velocity function and I were to integrate it, or if I were to integrate my velocity function, you guys learn that this is the derivative of position. So when I integrate a derivative, I get the position function back. So I would get s of b minus s of a. Well, and that's the fundamental theorem of calculus, right? That's exactly how you find the fundamental theorem of calculus. Well, let me do this. To give myself a little bit more room, I just rewrote what we just wrote right here. So when we integrate velocity, we get position back, s of b minus s of a. And so let me go ahead and solve for s of b. Okay, let's go ahead and solve for s of b. So s of b is going to be equal to, so again, if I just move this over, right, so all I have to do is move s of a over. So it's going to be s of a plus the integration of a to b of v t dt. And you guys can see, again, this is the total change theorem. So my final position, right, this is my final position, is equal to, well, where did I start? My initial position, right, my initial position. And then I'm going to add the total change of what happens as I go from point A literally to point B. Remember, this is telling me my change. This is a direction. So forward, backwards, up, and down. So that's what this is. So that's what we're doing right here. So if you guys look back at the equation that we have here, that's why you see what you see here. The final position is equal to the initial position plus our total change. We'll get to displacement in a second. And then again, here, we can do the same thing with when we actually integrate acceleration. When we get acceleration, we're going to get v of a, well, v of t of 2 minus v of t of 1. Well, if I move it over, I get that my final velocity is equal to my initial velocity plus my total change. So that's actually really awesome that we can look at it like that. Let's really quickly talk about displacement for a second. So there's a reason why I wrote this up here on the page is that displacement, so what you guys are now going to know is displacement is just the integration of vt dt. And that's why, which is what this is right here, right? But you guys learned in particle motion that displacement really is just where we finished up minus where we started. So this is what we talked about when we actually were doing particle motion. We described displacement as s of b minus s of a. Well, now you guys know from the fundamental theorem of calculus that these are equal to each other. So now we know displacement can be rewritten not only as s of b minus s of a, but also as the integration from a to b of v of t dt, which is really awesome. And then the only thing else I got to talk about really quickly before we start getting into questions is our distance. And for distance, we want to look at it, and it's just going to be the absolute value, not the absolute value. Well, it's going to be the absolute value of velocity, which is basically the integration of speed. So what I'd like to say really quickly is we come up here and we start walking and we have a positive velocity, and then we start getting to a point where we have negative velocity. We're starting to walk downward and backwards, and then we keep walking negative, negative, and we go positive, positive, and then we eventually get back to our starting point. Well, our displacement is actually 0, right? It's how far we went from the start to the finish. We ended up at the same spot. But our distance is all of these velocity values, but we're taking the positive of them because we actually, no matter if we're going forward or backwards, we're still going, we're still moving. So all of this is actually being added together. So even though our velocity is negative here, that's why we have to take the absolute value of it, because we really want to get this full distance right here. So that's really all that we need to know, ladies and gentlemen, to actually start this lesson. So before we get to actually better, crazier examples, we want to start with something that's pretty basic, just a visual, because we like visuals, on the difference between distance and displacement in a graph. So let's look at question number 4. 4 says a particle moves along the y-axis with the velocity v of t. And so like many times before, I've told you guys that it's really important to just focus on what graph we're given. So in this case, we're given the graph of v of t on the interval from 0 to 5. The graph of VT is shown to the right with the positive areas indicated by P, Q, and R. Notice that again, all of our areas are positive. It's just that when we're underneath the x-axis, that our rate of change is actually negative, right? Our rate of change is actually negative. What is the difference between the distance of the particle and then its displacement? So we want to look at for the difference. So the first thing is, since it asks us between the distance and the displacement, we're going to start with the distance because that's the first part of the question. So distance. So the distance is going to be equal to the integral from 0 to 5 of our absolute value of v of t dt. And, I just want to write that several times so you guys get used to writing that, so you know that when you see notation that's what we're going to want to see on your paper. So from here to here, our total change is going to be the area under this curve, right? That's going to be really what it represents. So how our function's changing over this time. So that's going to end up giving us p. We actually are given that area. And then because this is distance, we're going another distance of q, right? So we're going to go ahead and add ourselves a q. We're going to go ahead and add ourselves another q to get part of that. And then we're going to, because it's distance, we're going to go ahead and add ourselves the r. Because remember, even if we're going backwards, which we're going here and here, doesn't mean that we're still not traveling, right? We're still going an actual distance. So we have this. So our distance is actually going to be equal to the expression for our distance is going to be equal to p plus 2q plus r. Okay, so that's our distance. Let me go ahead and do something really fast. Okay, so I want to get this erased. So this is going to be our distance. And so let's look at our displacement. All right, so displacement is going to be very similar to our distance. We're going to integrate from 0 to 5, but of just vt dt. And the one thing I actually forgot to mention really quickly that just popped in my head is that this right here is usually a calculator problem. Our total distance is usually a calculator where you have to put in the absolute value. There is a question I'm going to do for you guys a little bit later on that shows you how to do it without the calculator. It's a little bit of a pain, but it's still doable. So just preface you by that. So usually like these questions are going to be calculator because it's really hard to do an absolute value function, integrate absolute value function without knowing what the function is. But all right, so let's go back to this question. So 0 to 5. So again, we're going to look at P. And then just here's a strategy for a second. So guys, I want you to see right here that we have the same area in the top and the bottom. If we're really trying to figure out what's going on, what our total change is, these actually balance each other out. They cancel each other out. So I can technically write minus Q plus Q here, but I don't really have to. So when we start talking about area under the curve some more, especially when we get to absolute extrema, it's really important for us to notice that we don't have to waste our time finding the area of this and finding the area of this because they're going to cancel each other out, especially if we're on this interval. So again, that's just a little strategy that I just want to talk about. And then we're going to go ahead and subtract r, right? Subtract r. So then our displacement is going to be p minus r. P minus r. And then so our final answer is going to be what you see here. What's the difference between the distance? So it's going to be p plus 2q plus r minus, be careful with our parentheses, minus p minus r. All right, so p minus r. So this is going to be equal to p plus 2q plus r minus p, and this can be plus r. Plus r. And so what's going to happen here? The p's are going to cancel, and we're going to be given 2q plus 2r. So our answer is going to be letter E. Okay, letter E. So there's, again, a very simplistic problem where you guys can see the distance versus displacement idea. All right, so for question number 5, it says the acceleration of a body moving in a straight line is given by this acceleration function right here. If the velocity of the body is 25 at time equals 1, and if s is a distance of the body from the original time, what is s of 4 minus s of 2? Okay, so the first thing we want to do is we're given some information about velocity, and we're given the acceleration function. So we want to go ahead and integrate our velocity function. So we're going to go ahead and integrate, the acceleration function. We're going to get 8 minus 6t dt. And when we integrate this, right, then we're really going to get velocity back out. So our goal is to get velocity back out. So this is just going to be an 8t minus 3t squared. Okay, and then we would again have a plus c, right, a plus c for that. So what we're going to say here is if the velocity is equal to 25, remember this is equal to actually v sub t. Let's go ahead and write that down. So v sub t. So it's telling me that if the velocity is 25 when time is equal to 1, right, so this basically means that v of t is equal to 1. So v of 1 is equal to 25, v of 1 is equal to 25. I can go ahead and just plug in and find what my c is, right? I can find my c very easily. So c is going to be equal to 25 minus 5, which is going to be equal to 20. It's going to be equal to 20. So my velocity is going to be equal to, my velocity is going to be equal to 8t minus 3t squared plus 20. Okay, so let's continue on with this problem. Now, what we're looking for is what is s of 4 minus s of 2? Well, we already know, ladies and gentlemen, that because of what I said at the beginning of this lesson, that s of 4 minus s of 2 will be equal to, it's going to be equal to the integration of our velocity from 4 to 2. We know this is going to be equal to that, right? We know it's going to be equal to that because that's going to give us our position function back. So all we have to do is integrate from 4 to 2, 8t minus 3t squared plus 20 dt. And once we do that, and again, this is probably going to most likely be like a calculated question, even though it was in 1973, because this is a lot of work. It's a lot of work for this question, but we're going to go ahead. I assume you guys know how to simplify this. This lesson is not fundamental thermodynamic calculus, so when you integrate this problem, you get 32. Okay, 32. So the point of this question was just to remember that if you're asked for a displacement, this question could have also been asked, what's the displacement of our function on the interval from 2 to 4? Okay, so just knowing that this is equal to this, and again, we had that conversation right up here, Okay, so let's look at another example. The particle moves along the x-axis, so the velocity is given by our function here. At time equals 0, the particle is at position 0.05. So that's our initial thing. So that says that s of 0 is equal to 0.5. But again, ladies and gentlemen, this is where we're starting, 0.5. But what's the total distance the particle travels from 0 to 3? From 0 to 3. So this is another question that we do not care about the initial. If it said, you know, where is it located at time equals 3, then yes, we care where we started. But we don't care about that. We can be starting anywhere. We can start anywhere. So all we have to do for this question, and this is just straightforward, 0 to 3, you have to remember though, when you write these questions out, that you have to put the absolute value of your velocity, because that's what we're looking for. All right, so let's go ahead and get our calculator out and show you guys how to do this one. Okay, so I went ahead and put our function in, all right, and which is very easy to do. So our function is, you know, what you see right here on the calculator. And then I go ahead and quit. And then once you hit math and you hit 9, all right, math 9, then we're going to integrate from 0 to 3. And then there's a couple things you can do here, but the easiest way to do this is go math again, go all the way over to numbers and press 1 for the absolute value. And then what we want to do is then go to alpha and then to trace. And we made sure you guys remember that we did this in Y1. So we're going to go ahead and click on Y1. That way you don't have to waste the whole time typing the question in. And again, I keep talking about FRQs. This question may have multiple parts to it, and we don't want to have to type this in every single time we do it. We go ahead and press X, but again, do not forget about the absolute value. That's really, really, really important here. And we're going to see that our answer is going to be equal to, as our calculator takes a little bit of time, 4.181. So 4.181, and it is answer choice D. Okay, so that is that one. Again, please do not forget about the absolute value on this problem. Okay, so let's move on to another question. See what you guys think. Okay with this. So question number 7. So now this one right here is the velocity of the particle moving on the line at time equals t. So I'm not going to do this question, but I do want to talk about it for a second. And it's giving us problems, and it says how many meters did the particle travel from 0 to 4? So again, this is another question that's distance. Okay, and this is a non-calculator question. This is a non-calculator question because, again, this was question number 14 in 1985. So what we want to do here for distance is we want to go from 0 to 4 of our velocity function, but we want to take its absolute value of d of t. Now, I'm going to show you guys in a second why when we do this without a calculator, I want to show you guys what we need to do. But for this one, we can actually drop the absolute value for this particular function. That's what I was trying to say when I was mumbling earlier, so I apologize about that. Because this function is always positive. Look at it. It's always positive. We don't have to worry about where it's negative because it's always positive. Our exponents are whenever we do it, we're always going to have it to 1/2 power. So that means it's a square root. 3/2 power, I can pull out a t. I still got a t underneath the radical, so it's always positive. So this function is always going to be positive. So I can actually get rid of the absolute value. So our displacement is actually equal to our distance in this problem. And so again, you integrate this the old-fashioned way, and then you get the answer is 80. The answer is 80. Again, fundamental theorem of calculus is how you do that problem. All right, we got one more video, or one more example I want to show you guys in this video, and then we're going to move on to another one. But this one I like because, again, it's a calculator question, and it's really just very subtle on what we have to do for these problems because of just listening to the verbiage of what we have to say here. So the particle moves along the x-axis such that the velocity is given by the function sine of the absolute value of t. So again, we're given the velocity function for the interval from 0 to 100. The graph of v of t is shown to the right. The position of the particle at time equals t at time equals 0 is this function right here. So again, I like s better than z or x, so I'm going to go ahead and write that out. So that's my initial. Find the distance traveled from the particle from 0 to 100. So we should be getting really good at distance, right? So we just know that from 0 to 10 or 100, 0 to 100, we're going to take the and this is a calculator problem. So we're going to take the absolute value of v of t, and we're just going to plug in. So what you would plug on your calculator is really just the absolute value of sine of the absolute value of t on your calculator. And then you're going to get 59.705, okay, units, whatever this is that we're looking at right here. For question number B, letter B, it's asking us for the position at time equals 100. So this is total change. This is total change. So for this one, we have to talk about the initial because we want to know where is it? Where is it? So our position, so s of 100 is going to be equal to s of 0 plus our displacement, right? Our displacement, because we need to take into account whether we're going backwards and forwards. So we want our displacement for this. So s of 100 is going to be equal to our initial, which is 10, plus, in the calculator, 0 from 10, and this is the non-absolute value of this function. And that's our displacement. So hopefully that makes sense. It's where we started plus what our displacement is. So if we started walking backwards, yeah, that's going to affect our final position. And so when we plug this into our calculator and we add 10, we get 25.693. And so that's going to be the total. That's where our position is. So this is how much we've traveled, and this is where we finally are. Okay, based on the fact that some of this we did go backwards or down, whatever you want to think about. All right, ladies and gentlemen, that's our first video for rectilinear motion. Hopefully that made sense. We're going to come back and do one more video for you guys in this lesson, so I'll see you guys in the third video.